Okay, so we discussed something about basic topologies. Now, since we know a lot about already like the basic spaces, now we're going to use it to talk more about how we can use this. Like basically, we're going to be talking about functions and the property of continuity to know about it, which is very important. Oh, I actually did a limit function here too, so not sure why I did there as well. So I'm just going to go very fast. So we already talked about this limit function, right? So basically, oh, I wrote it correctly here. So see, I wrote it as q. So it should be like q because we don't know if f is going to be defined at that point. So it's exactly similar as the one we did before, except we're saying this is q. Fx goes to q because there are some, we can define a limit even if their point is not defined at the point q. That's why you do this. And so it's all same, but instead of writing it very long or fx going to q using like an arrow mark, a lot of the time we use this notation, which is limit a, x goes to a, fx goes to q. So, and related to the limit definition of limit, there comes the definition of continuity, which is very similar to limit, but it's a little bit different. So you can kind of see how it goes. So since functions basically is a bridge or mapping between two metric spaces, we need to define metric spaces first. So we're supposing there's an x and y, which are metric spaces, and E is a subset of x, and P is element A, and F maps E to Y. So basically, like there's an x, there's y. Basically what we're saying is that this function maps this part, E, into the y, like this. Then we say that f is continuous at the point P, which is inside here. We say it's continuous at point P if there exists, for every epsilon, there exists delta such that, well, the similar notation like limits, like if fx minus fp is smaller than epsilon, then every point that is close enough to P is going to make sure that the value is distance is going to be smaller than epsilon. It's kind of similar to the concept of limit. So it's very exactly similar, except the difference you can see is that when we define the limit, we define q, right? We didn't say the q has a point. Q can be, there's a point where in the function where you can get the point q, right? But in the continuity, the difference is that we actually define that this point is actually can be defined by the function. So we write fp instead of q here, right? You can see that we used to write this part q, but now it's fp because we know this function exists, at least in the definition of continuity. So f has to be defined at the point P in order to say something is continuous at P, which is very intuitive. Like we wouldn't want to have a part where limit exists, but this point is like not defined. We don't say this is continuous, right? There's like a hole. So continuity definition is making sure this point is like defined. So, and some like basic nice thing to know about composition. So composition of functions basically mean you're just like concatenating like functions together. You're just like grouping them together. So right here, now we need to have three metric spaces, x, y, z. So what we're thinking is that f map E from y, but we now have another metric space, and there's a function g that maps this part, where fe is going to be inside here. And g maps this to here, like two-way, right? And if this is like the composition definition. So basically, what we're doing is that we're connecting two functions to make sure that if it's defined here, it's also going to have the value here by doing that notation. I think you're already probably familiar because you have already seen this in calculus, especially if you do a lot of like chain rule differentiation, which you're not going to talk about too much. They always talk about these sort of definition of composition of functions, right? I wrote this because, remember like the definition we used here? This is one definition of a continuity of function. And this is another way to define a function is continuous. And I wrote this because a few reasons. Because I mean, it's a very, sometimes like instead of using the first definition, it's a lot better if you use second definition to show something's continuous. And also because it's more abstract, because we can use the sense of open sets to show that something's continuous. But you can use both definition anyway. So I just wrote this. So 1 and 2 are just similar. We say that if f is a function mapping x to y again, we say that the function is continuous if and only if the inverse image of v is open in X for every open set V. So what does this mean? So remember that the inverse image is like a, let's say this is V, right? And this is open set. So you choose any kind of open set here, and you use inverse to get this here. And you also get a set, right? And we're saying that for any open set here, this inverse image, this is going to be also open here. And if that holds, we say that the function f is continuous. Even though it kind of feels like so different from the first definition, in the fundamental sense, they're both equivalent. Just note that. Actually, like, this is a bit more general definition of continuity, to be exact. So we come from here to the first definition, but it's not very important. So, and the continuity definition, second one is just similar, except instead of doing open set, we say closed set. So for any closed set here, inverse image is also closed here. If you can show this, then it also shows that f is continuous, right? So that's a very nice definition you might know, and if you know, it's very useful sometimes because it's a lot easier in proving some things. And if you want to know about like the more direct reason why they're connected or they're equivalent, you can also check the textbook. They have a nice proof about it. All right. And again, we said sequence is bounded. We say some set is bounded, and we also can say a function is bounded. But function being bounded is more intuitive in our knowledge because basically what this means is that there's some element where the function's value cannot pass, like the famous xy graph again. It's like xy graph. Let's say function is going like this, and sometimes you can get some m value here. If this function does not go over here, and if m is finite, we say this means function is bounded. More intuitive, right? And that's in a more rigorous notation here. So we say that a function is bounded if there is some real number m such that the absolute value of x is smaller than this. So far, so good. So, and the reason we kind of learn about continuity, we'll see from the title, is that actually continuity is very nicely related to compactness. So continuity is not just about being the property of being connected. What it means is that continuity preserves compactness. So what does this mean? So we did this again, so I'll just use this. So what that theorem is telling us here is this. So we have x and y, a function mapping a, now let's say this is compact set here. And this function maps compact set here, right? And there will be some sort of image of the compact set. And what this tells us is that continuity preserves compactness. That is, if this is compact here, and if f is continuous, this set here is also going to be compact here. So the property of compactness is preserved by the continuity. That's why function is very important, because especially the continuity concept, because it preserves a lot of the good properties into other sets. So that's basically what it says in the definition here. So suppose f is a continuous mapping of a compact metric space x into metric space y. Then fx is compact. So it makes the compact set and it preserves it, even though we transfer it from one space to another, which is a very nice quality, right? Oh, sorry. I also wrote some proof here. Let me just briefly go through this to kind of show how it works. So it's also, and again, like proving things also always goes by definition. So let me just read it through. Like, we want to show that fx is compact, right? So basically what we're going to do is in the end, we're going to show that every open covering of fx is going to be having a finite subcover, right? That's like the definition and the goal we're trying to go. So we assume that V alpha is like a set of all open cover of fx, right? And since f is continuous, we use, remember this theorem? That's why it's very handy. Because because f is continuous, we know that from the formal theorem that each of the inverses of these open sets are going to be open, right? So what we're doing is like we're like doing it backward. So this is fx. So and what we're trying to do is that we're trying to have an open covering here, right? That covers fx, and these are called V alpha here. And what we're doing is we're just getting the inverses into this region, like this. And they're also open, because VA is open here. Continuity says the inverse is going to be open. So we're coming here, we're starting from here to here. So F inverse V alpha is going to be open. And because we said that X is compact, right? And there are finitely many, so there are going to be finite and many indexes such that X is going to be covered by them. So remember that in this case, X is like all going inside here. So, and we had an open covering for this set. So if you get an inverse, these open sets are also going to cover X. And remember that they're open because X is compact. We can take a finite subcover out of them to make we can still use it as an open covering, right? Then, since we know that if we put the inverses back into Y, it's going to cover E. So what we're doing is that we're using the concept of compactness here and use it to bring it back to find a finite subcover for the FE. So then for every E, this means that fx is basically a subset of some finite subcover. Finite subcover. So this is kind of very nice. I think it's a very nice proof to know about. So basically, because of this property, we can show that Y is continuous used often because it's a very nice property that conserves and preserves a lot of the good properties such as continuity. And not only that, though. Oh, this is a corollary because it's very. There's a typo, UF. I'm not sure why it's there, but just ignore that. I think it's if. So if F is a continuous mapping of a compact metric space X into R, then fx is closed and bounded. You might wonder why. It's because, like compact is equivalent to closed and bounded in R. So in this case, compact means just closed and bounded. So that's why this corollary holds. Just know that. And you might wonder, why are we using this compact preserving thing? When is this used? You might not remember this now, but remember when I showed you where sometimes use analysis concept in economic theory? You remember thinking of, I'm not sure if you remember it, but there was a part where say we want to show that the function has a minimum, right? And we try to show that it attains a minimum value or maximum value for a cost minimization function. And there was a saying in the answer part where you kind of had to show that f is continuous, and because the set is compact, it's going to attain the maximum or minimum inside there, right? Actually, that's possible because we're using the concept of continuity and compactness. And that comes out right here. So it's called extreme value theorem. 한국말로는 최대 최소 정리일까요? 뭐 최대 최소 정리라고 불리지 않을까 싶긴 한데 잘은 모르겠습니다, 사실. 그래서 하여튼 extreme value theorem이라는 게 있는데, so basically what this means is that if f is a continuous function in a compact domain set, then it attains minimum and maximum. So as long as this is very interesting. So as long as x is compact and f is continuous, I mean, even though you don't know which point is going to be maximum and which point is going to be minimum of this, you can still ensure there's going to be a point where it's going to attain maximum and minimum by using the fact that this is compact. A very nice property. So in our economic question, there was a part about where we had to find the cost minimization part. And if there indeed is a combination of labor and capital that really does attains the minimum value, And in the problem, how the person solved it was to show that because f, the cost function, is a continuous function, and the set of the domain was compact. By showing this, he kind of showed that the answer, that there will be some point where the cost is going to be minimized. That's why it's used, right? And it's very, and these kind of ideas are also very used frequently in economics, in like micro theory classes, so just be aware. And I wrote down like more rigorous theorem here for extreme value theorem, which is, so f is a continuous function on the compact matrix set. Then there are going to be some point P and Q such that this holds basically means minimum maximum, right? Minimum maximum. So basically it holds, contains the maximum minimum. That's why we use, that's why this continuity and compact properties are very important. All right. And there's the continuity and connectedness. Actually, this might be more familiar to you. Remember, like the intermediate value theorem, like in Korean, it would be 중간값 정리, which is, you might learn in the calculus courses that we always have a part where, like, because fx is continuous, I'm not exactly sure how it was written there, but something like if there's like a continuous function for any value y between here, you say like there's going to be some point x here, right? It's very intuitive, but if you remember like the Stewart calculus book or other calculus basic courses, they'll say something like this looks very trivial and obvious, but to show why this holds is actually very hard and needs some understanding of analysis, and this is why, and this is why it holds. It's due to the continuity and the property of connectedness, which is called the general intermediate value theorem, which is just like a special case for the ones we use here. I mean, more general case. So basically what this means is that if F is a continuous mapping of a metric space X into metric space Y, and E is connected, then FE inverse, FE image is going to be connected as well. It's the same as compact, right? So there's X, there's Y. Oh, right. Attendance code 55. Okay, the attendance code is 55. Appreciate. 그래서, so there's X and Y, and there's a continuous function mapping again set E into the Y. Remember that if E was compact, this was also compact, right? Now, if E is connected, it also preserves connectedness. FE is also connected. That's very interesting. So I did write down the proof, but it's not that important. You can just check it out. So what this basically means, that continuity is important because it also preserves the property of connectedness into the other space. So, and just look at the proof if you want to check it out. So now we have the intermediate value theorem with it. So using the continuity and connectedness property, we can show that actually intermediate value theorem holds. So let f be a continuous real function on an interval ab, and if fa and fb are such that fb is bigger than fa, and c is such a number such that it's between fa and fb, there's going to be a point x where fx is going to be c. And this holds because the connectivity. Can kind of see like AB as the domain. This is connected, right? So the function, if it's continuous, is FAB. It's going to be connected. It'll be something like this, right? This point value. Oh, let me just write it more like y. So what this literally means, because AB is connected, the value FAB is going to be some sort of like connected line, the values. So there has to be some point where there's some x that goes here. Because if that doesn't work, which means there's some point where there's no point here, this means this space is not going to be connected because there's like a hole here. So this means like this will mean that the space is not connected, And due to the continuity property, this means that this has to be disconnected, which is impossible. So that's why it shows that the intermediate value holds using the property of continuity and connectedness. That's why actually like compactness and continuity properties are important. Like it's like usually used with continuity of a function to show that certain properties are preserved in the function. Any questions? 질문 있나요? 없으면 여기까지 하겠습니다. So we'll end the session today, and tomorrow we'll go for some very basic brief differentiation, and then we'll just go on for linear algebra.